It's a great pleasure for me to be part of this panel on probability and statistics. And the aspect that I thought I will talk about today has to do with extreme value statistics, meaning the statistics of events that are either, at the extremes, very large or very small, and what they can tell us in systems which are of interest to statistical physics. In particular, in statistical physics, we are often interested in systems which approach or reach an ordered state. And I would like to see and like to talk about how extreme value statistics can really help us understand the approach to an ordered state. Okay, to start with, just an introductory slide. So, why are we interested in extremes at all? Well, the maximum of a set of variables, which is like an extreme, often is a good measure of an extreme event. I mean, think about a flood, or think about a drought, or a collapse of a bridge. These are extremely catastrophic events. Measures like if you're thinking of a flood, the height of the water in a river is a good measure of a measure whose largest value will point towards maybe a flood about to occur or not. Anyway, so the question of interest to us is how likely is it that we actually get to these largest values, and to answer this, we'll talk about the distribution or equivalently the probability density of these maxima. So here's a picture, and you see, let's say these are random variables which are taking various values. We're familiar with the idea of an average or the mean, which is a very familiar concept to all of us. But here is one guy who sticks out, is the largest, and this is the maximum. The question is, how likely is it that you have a particular maximum value? Now, the answer depends very much on whether these are independent of each other or whether these variables are correlated. If they're independent, then in fact there are very old and classic and important results on these distributions, and I'll tell you about some of these. But the interesting thing is what happens if these get strongly correlated and they influence each other. What happens to the maximum in that case? This is the sort of question I'll ask about. So here's an outline of the talk. I'll begin by talking about independent variables, the case of independent variables, and then you'll see that there are extreme value distributions, in other words, distributions which govern the values of these extreme events, and these are universal. Universal in a sense that I'll describe. On the other hand, with correlations, the distributions turn out to be very different. Not surprising, but it's good that we can actually say something about these. As we move towards an ordered state in statistical physics, an ordered state is extremely correlated, so these correlations build up in time. And the question would be, how do these change in time? And I'll try to answer these within the ambit of a simple model of interacting particles called the zero range process. So here, in brief, is the scenario. Zero time, early times, system uncorrelated. But as time passes, it's approaching an ordered state. It's getting strongly correlated. We know that when it's uncorrelated, it's described by one of these universal forms. We also know that when it reaches the end, it has a substantially different form. The question I'm going to address really in the end is what happens in between. As time passes, how do these distributions evolve in time? Turns out that these EVDs, as they are called, EVD is an acronym, it's extreme value distributions. I'll just call it EVD. EVDs are very sensitive probes of what is happening in the dynamics. This process is known as coarsening. I mean, as you go from uncorrelated to correlated. And in fact, as you'll see in the case that we'll study, they even pinpoint, the EVDs pinpoint a new dynamic regime. First of all, the notion of universality. This is actually very familiar to all of us. If we are dealing not with the maxima, but if we are dealing with the average values of a set of variables, here we are. So here's a set, here's another realization of that set, and so on and so forth. And here are these mean values, which then self-fluctuate as we go from one realization to the other. And the question is, if we ask for the sum of the variables in this in one box and the other, from one to the other, the question is, what is the distribution of this sum? And the answer is very well known. The answer is a universal answer, more or less independent of the initial distribution of the random variables that we had, so long as they're uncorrelated. Okay, so the answer is indeed that the sum is distributed as through the normal distribution, a Gaussian, whose mean and variance are governed by properties of the initial distribution. If it happens that the variance does not exist, if the initial distribution is very broad, even then we know what the answers are. They're they're drawn from the set of Levy distributions, well-known stable distributions with a certain index alpha, which depends on the tail of the distribution. The point I'm trying to make is that there are universal distributions independent of the original values for the means. Likewise, for the maximum, it turns out there are universal distributions again. For instance, if we have an initial distribution P of x, it's quite evident that if you draw n times, capital N times from this distribution, then the probability that the maximum lies below x is given by a formula of this sort, because these variables are uncorrelated. Turns out that analysis of this form yields the result that there's a final limiting form which is independent of the details of P of x. So this capital P of z, which is the final form, is an example of an extreme value distribution, and I've drawn one of them to conform with what I have upstairs here. Then there are three families of such distributions: the Frechet, Gumbel, and Weibull distributions. And they're so important overall that I felt that I must show you at least what they look like. Here they are, Frechet, Gumbel, and Weibull. The Frechet distribution arises if the initial distribution has a power law tail, and the final universal form also has a power law tail, 1 over z to the alpha plus 1. The Gumbel arises typically if you have a distribution that decays faster than a power law, and in which case exponential of an exponential form, which is put down here. And the last distribution is the Weibull distribution, which has to do with bounded distributions. Here, the bound is a lower bound that I've put in here. The point is that these are universal distributions, well characterized, provided the variables we're talking about are independent. However, we know that in real life, things are not necessarily independent, and there are often sources of correlations. And the question is, how do these influence the maximum value? Well, so to start with just three simple examples of how correlations may arise, they could come from shared histories in time. What do I mean by that? For instance, if you have a random walker which has reached a particular position at time t, obviously the location at time t plus 1 is very correlated to where it was at time t. Anyway, it turns out that if you ask for the in a one-dimensional random walk, if you ask for the extreme value, the largest distance away from the origin that you have moved, that's given actually by a Gaussian with a theta function, which limits the Gaussian to be on the right. Okay, another physical example where interactions occur, and so the variables are correlated, have to do with an interface. And the interface, is drawn in red here. If I look at the height at different locations as random variables, they're definitely correlated because of surface tension. So surface tension will prohibit very large variations and therefore give an indirect interaction between the random variable here and there. Lastly, you may have a constraint which coming from a conservation law. For instance, I mean, if you have simple conservation of number of particles, here is an example of some stochastic model of movement of particles, that things are moving up and down, but conserving the number of particles. In that case, the fact that you have a conservation law implies a constraint, and that limits, or it correlates fluctuations at one point, with those at another, and therefore we can assert, clearly that these constraints coming from conservation laws in fact lead to correlations. So these are three examples that I thought I would tell you about. Now, the other bit of the other stream that I would like to develop before I talk about a specific model is the following. Question is, how does order develop in time? Now, it's a very broad question, so let's just think about a specific example. Suppose I have a magnetic system or an Ising model, as it's called, which will, in its equilibrium state, have two phases. Let's say majority spins up and majority spins down. However, suppose I start dynamically in time with a random initial condition. The question is, how will I reach this ordered steady state, this phase ordered steady state? And the answer is that what happens is a process which is called coarsening. So look at these pictures. These are from a Monte Carlo simulation. At 0 time, there's very little correlation between black and white, black representing up spins, white representing down spins. But as time passes, you see that the pattern gets a little coarser. You can see there are clumps of black and clumps of white. So what is happening is that the phases are beginning to form, but it takes time for this to happen. Well, time it takes, but in that time, what happens is that you develop a very natural length scale. So there's a length scale which grows in time, which describes the degree of order that has set in. So let's denote that length scale by the script L of t. Okay, it typically grows as a power law in time. And here's a schematic depiction. I mean, it says that at small times, this length scale is relatively small. So you can see these brackets, each one depicts L of T1, but as T1 becomes T2, of course, L of T2 becomes bigger, and the ordered phases within each script L themselves become larger. So reflecting what is happening in these pictures, I've just put down a schematic here. And finally, if you have a finite system size, capital L, once this L of t reaches capital L, okay, you've reached your final destination. You've reached equilibrium or you've reached steady state, and then the system will not evolve substantially. Now, this picture, there's good evidence for this, and it turns out that it's mainly through the study of 2-point correlation functions that of this sort here that I've put down here, n of 0t, n of rt. This is what we traditionally call a correlation function, and subtract of the mean value squared. This correlation function turns out to be a function of L of t, that same L of t that I talked about. So what is L of t? It's nothing very mysterious. I mean, it's as we go from initial to intermediate to long times, it's basically the size of the droplet of the other phase that's of the phases that are growing in time, and that basically sets a length scale, and correlation functions turn out to scale with that time. Here's an illustration from a simulation. Many correlation functions measured at different times all collapse onto one, universal curve if if space is scaled by L of t. So there's no doubt that this quantity L of t not only exists, it plays a central role in the ordering phenomenon. Okay, so let me take a stock for a minute. Where are we? What have we said? Well, we've said that we are really interested in extreme value distributions, and it has one of three universal forms if the variables are independent. If they're correlated, there are new distributions which emerge, and we've also seen that there is this process of coarsening which allows correlations to spread. So if correlations have not spread very much, we expect extreme distributions will be like almost independent. But if they spread a lot, then up to a certain length scale, they will be correlated. The question is, how do these distributions evolve during coarsening? This is what I would like to address. So to do that, I'll take up a case study. This has to do with coarsening in the zero range process. I'll define the model. And my collaborators are two young people at TIFR Hyderabad, Chandrasekhar Iyer and Arga Das. Chandrasekhar is visiting from CEBS Bombay, doing his master's thesis here. And we've been working on these problems. I'll tell you a little bit about what we find. First of all, we confirm the idea that there is a growing length scale, rose as a power law. Second, that within this length scale, as you might expect, there are strong correlations. Okay, and these are reflected in the distribution of extremes. Correlations between regions are weak. Turns out this sort of analysis actually pinpoints something that we certainly did not know about or expect, namely a new dynamic regime, which has sort of important implications in coarsening. Okay. Now, let me then tell you a little bit about this specific model, because A, it is interesting in its own right, and B, looking at a particular model really helps to focus the sort of slightly more general ideas that I've talked about already. So first of all, let me tell you what the zero range process is. It's a model of, it's what's called there's a phrase used, interacting particle system. I mean, so these are particles, these small boxes are supposed to be particles, and they're moving around stochastically. In the model that I'm describing, they move only towards the right. But the rate and they move, meaning, I mean, if you have at one place here, you like here you have four particles, but only one particle can move at a time. Okay, so, but the rate at which it moves depends on how many particles there are. Since there are four here, this guy will move at a different rate from when there are, like from here, there are only two particles. So U of 2 is the rate at which this particle moves. U of 4 is the rate at which this particle moves. And you can allow for arbitrary functional dependencies of U on the number of particles. For instance, here's a big fat tower of 10 particles, and this top guy will move with the rate U of 10. You can cast this in the language of stochastic processes through master equation, etc., etc. But I mean, these are the essential moves. Interestingly, the zero range process can also be viewed in a completely different context as a model of traffic. If you reinterpret these masses, these towers, as headways between cars. I won't elaborate on this analogy, but it's a very interesting and useful avatar of the zero range process. We'll talk only in terms of these moving masses. I mean, and they're chipping. I mean, one thing chips off and moves. And when it chips off and moves, it combines with the whatever's on the right. Like this guy moving here will make a four particle cluster and leave only one there. Okay, so I hope the moves are clear. Now, I won't give you the proof, but I'll tell you that the steady state of this model is known. What do we mean by when we say the steady state is known? What we mean is that if you give me a set of particle numbers at different sites, 2, 1, 3, etc., I can tell you the probability for that configuration to occur. Here it is. I mean, so there's an explicit formula in terms of the rates that you had to start with. Fine. So now you might think this is just one more of these solvable models. Yes, of course it is, but it's very interesting. The reason it's so interesting is that it shows the phase transition. What happens for a particular choice of these hopping rates is that there's this transition from a so-called normal state, which looks like this, to an aggregate state. Now, this aggregate state is quite remarkable. One site in the full lattice, you can't predict which one, will hold a macroscopic number of particles. Macroscopic simply means that a finite fraction of an Avogadro number of particles, a finite fraction of them land up at one site, a fraction. Of course, the rest of them are distributed as usual. So it's a real space analog of Bose-Einstein condensation. Bose-Einstein condensation, as we know, occurs in momentum space. It's a macroscopic occupancy of the zero momentum state, and leads to superfluidity and so on and so forth. This is, of course, nothing like that, but it is like that in the sense that one site, rather than one momentum state, has a very large occupancy. So this happens if the overall density of particles, meaning the total number of particles divided by the number of sites, if that exceeds a certain critical value, rho c. Okay, so these are well-known properties of this model. So let me come back to my question. My question has to do with extreme value distributions. So I have now in my hand a model which has a phase in which the distribution of, let's say, these clusters of particles is exponentially decaying. But as I change the overall density, it goes to a critical state where the decay is a power law decay, and finally to an aggregate state where I have a single place, a single site with a very large number of sites. So clearly, if I'm looking at the extremal value, the largest value, this will be a very good way to study the condensate, as I'm calling the particles on this site, which have piled up in this very unusual way. Right. Recall, of course, that we have this constraint that the sum of all the particles is fixed, because no particle is created or destroyed in the process. This number is fixed. And remember that constraints imply correlations. So at the end, when we have this blue state, the condensate state here, this is actually a strongly correlated state. So the correlated state is, leads to the following, feature. Turns out you can actually characterize the full distribution of mass in this state. It's not one of the three universal forms because of the strong correlations. It turns out that it's a Gaussian in some regime of the parameters, and it's not a Gaussian but can be characterized in another regime. So there's a very nice paper by Martin Evans, Satya Majumdar, and Royce Shea a few years back, which establishes this. Okay, so right. Okay, right. So let me march ahead. So recall this distribution, this condensate phase, this new distribution refers to the condensate in the steady state. In other words, if I have a system and I've given it infinite amount of time to settle down into its state, this is the state that it would reach. Now let me ask the question I really want to, which is the following, which I alluded to earlier, but now we will come back to it in the context of this model. The question is, sorry about that, random initial condition. Obviously, my particles are uncorrelated in that case. Okay, let me come back here. So we are starting at 0 time initially with a completely random initial condition, imitating, if you like, I mean, in phase transition context, infinite temperature, no correlations. Okay, so we have an uncorrelated state. If we have many variables with no correlation, we know how the largest of those is distributed. It's distributed via, I mean, the distribution follows a Gumbel distribution, one of the 3 universal forms I showed. So here's the result of a simulation. Indeed, it's totally a Gumbel. Now time is passing, coarsening is happening. Finally, you're landing up with this ordered steady state. It has strong correlations. And as we've seen, the prediction from the theory of Evans et al. Is that it should be Gaussian. And here are the results of simulation. It is indeed Gaussian. No surprise, it should be. Question is, what happens in between? Okay, so just to get a very quick idea, we take a tiny system and do a quick simulation. And what you find is that starting with a distribution like this, you quickly develop locally peaks. Here's a peak, here's a peak, here's a peak, no peak here, etc. So locally, the system is creating these mini condensates. Okay, the system doesn't know it's actually very large. So on some time scale that some length scale that it can reach, it quickly creates a condensate. But as time goes by, the extent of that region, which is that L of t, becomes larger. Each condensate becomes larger, but the number of condensates comes down. And finally, you'll end up with one condensate in the end, and that will be your steady state. Okay, very good. So let's then pose the question. So suppose indeed we have this very large system, and we think of partitioning it into boxes of size L of t, like this. In each box, I'll certainly have a largest value. Here it's the red one. In this, it's this red one, and so on and so on. So I have small maxima in each such region, but of course the regions are getting bigger as time passes. So across one bin to the other, there are very weak correlations, because correlations are spread only to L of t. Therefore, the maximum across all these bin maxima will, of course, give you the global maximum, which should be governed by a Gumbel, by one of the universal distributions. You expect that, right? And indeed, that's what's found. The only slight twist to it is that the number of bins depends on the time, because L of t is getting bigger. So the number of bins is decreasing. Now, what about within each bin? That is the interesting question. Well, there are very strong correlations. Now, what about the distribution of maxima within a bin? We know that in steady state, finally, the distribution is Gaussian, which is okay, and it has a mean and variance of order system size. Steady state has system size capital L. So naively, we might expect that within each bin, you'll imitate the steady state and you'll have a mean of order L of t and a variance of order L of t. But what actually happens? What actually happens is this. It's striking and it's very different. What happens is, first of all, so here are the mass distributions at different times. These numbers 78 to 227 are not times, they are the sizes of that L of t, which is increasing. So you can see this distribution is broadening. If I scale the mass by L of t, I get a perfect collapse of all these. So there is scaling at work. So these distributions, what we find therefore is that this mass distribution is actually a scaling function of L of t. But if it's a scaling function, then the variance which is the square of the standard deviation, should scale as the square of the mean. So it should scale like L of t squared. And this disagrees with the expectation based on steady state. See, the point is the following: there's a strong discrepancy here. Because L of t is going to expand and get bigger till it reaches system size. Now, we are saying here that the variance increases as L of t the whole squared. But it must latch on to the exact answer that it goes as order L. How can it do that when L of t becomes L? So to resolve this, we looked at the global maximum, and this is what we found. Here is the mean, here is the variance. So the mean actually behaves itself very well. It goes up and reaches the value it should reach. Likewise, for different system sizes. But look at the variance. Look at the time dependence. This is time. Starts at 0, it has to reach this value or that value depending on the size. It doesn't go in a nice monotonic way. No, it's non-monotonic and strongly and viciously non-monotonic. I mean, it exceeds the steady state value hugely, goes up and then comes down, and it reaches the final steady state. So before steady state is reached, in time, there's a new regime in which you have enormous fluctuations. It's a pre-asymptotic regime, different fluctuations, nothing to do with steady state. Oh, well, I shouldn't say nothing to do, but very little to do with steady state. What is this? Where does it come from? So let me give you a cartoon of what large fluctuation regime, unsuspected regime is. See, before the final steady state with a single thing is reached, we have a situation where you might have 2 or 3 of these very large maxima, very large condensates. Okay, finally, of course, it will become 1. But suppose there were 2. Now, these guys constantly exchange mass with each other. I'm saying mass, but I mean actually particle number through the bulk with each other. And as they do, their heights fluctuate up and down. So it's obvious that if you have 2 condensates, each of a certain fraction of size capital L, then the fluctuations of the sort I'm describing are also of order capital L. The standard deviation is of order capital L. The variance is of order capital L squared. So it's a huge it's a hugely fluctuating regime, and it's there. So what we learn is, first of all, there are these fluctuations, but what we are learning is that while the system is coarsening, while it is approaching steady state on the scales of L of t, the system emulates not the steady state, which is the normal lesson we learn in coarsening. It does not do that, but it actually emulates the pre-asymptotic strong fluctuation behavior. Okay. So I think, yeah, so you can ask, of course, does this happen in other systems? And there is another quite well-studied model called the mass shipping model. And indeed, the same analysis can be done there. This model is a model of moving masses and moving clusters. And indeed, the same or similar story is repeated there, with the variance showing a huge overshoot before it settles down to a steady state value. So with that, I'll conclude. What I've tried to tell you is 3 broad things. One, first of all, there is extreme value statistics, and the famous and universal results derived in the classic paper Fisher and Tippett continue to be of great importance. There are 3 universal forms, but the moment you have correlations between variables, these forms can change, and we've seen some examples of that. The other thing I told you initially is about coarsening. That the way it approaches an ordered state is by inventing or by making a new length scale, L of t, which depends on time, within which it has still an outside which it is not. Then we talked about coarsening in the zero range process, and we did see this evidence for strong correlations within L of t, and also for this pre-asymptotic regime with these, what I'm calling giant fluctuations. And these giant fluctuations are the ones which have an imprint on coarsening, not the final steady state. So the broad conclusions, I would say, are something like this: that extreme value distributions are, a subject of intense and intense study for many years, is now proving to be an invaluable tool to study time-dependent approach to a steady state, namely the process of coarsening. And one has to watch out and realize that the behavior within the coarsening length scale might be governed may not look like the steady state at all, but something else. Thank you.
Let me read out the question. The first one is from Sadiq Rangwala. Question is,
Yes.
what is going on with entropy during the coarse-graining process?
During the coarsening process, what is going on with entropy? Yeah, good question. I mean, let me think. Entropy, of course, must be increasing, and the way I guess it does so. Okay, not very clear to me at the moment. Does somebody from the audience have a good idea of this?
I'll move on to the second question.
Yes.
From Rahul Roy. Does the phase transition of ZRP suggest a preferential graph model?
I have to again admit in ignorance. What is the preferential graph model, please?
Rahul Roy, would you?
It is a graph where you add one vertex one at a time. Okay. And you add either a new with a certain probability, or you attach something to a place where there are X numbers. So according to the number of particles which are already there, the probability mass function is proportional to the number of particles which are already there. Therefore, you have a preferential attachment, and so it just blows up there. Whereas elsewhere, you have more or less a steady thing going on.
I see. Is this a dynamics in which you conserve the number?
No, you add the number. So at time n, you add an extra vertex.
So in that sense, this is a very different model, because the conservation here is playing a crucial role in the formation of the condensate. In a sense, if the condensate forms because the rest of the system is incapable of holding so many particles. So the excess is just thrown into that. So it sounds like it's different a little bit to me. I mean, the dynamics of the process.
Yeah, Mustansir, there is a question from Bhaskaran.
Yes. Right.
You discussed Ising order parameter in 2 dimensions, for example. Do you get new distributions in coarsening phenomena if you have XY or vector order parameter? Now you have topological point defects instead of line defects, like domain walls.
Yeah, so I think this is an excellent question which really deserves careful and proper study. To my knowledge, there is not very much study of extreme values of coarsening clusters in the usual models of phase transitions, but I think it's an extremely important question to, and indeed, as suggested by Bhaskaran, I mean, it's very likely that important differences will show up between the cases that you mentioned, XY to IISER, etc., etc. Right. So I think it has not been studied to the extent it should be.
Okay, I think there are more questions, but we have run out of time. So I will request Arup or Kapil to take this forward with the next speaker, please.
Thank you.